In this set of videos, I want to take us through kind of the final piece of the process dynamics section of the course. And what this really is we've gone through liquid residence time in a tank or a reactor, and we could apply our thermodynamic analysis that we've learned to a gas phase system. And we've also done those tanks in series and added a little bit of control methodology to that setup. And then we've also taken a look at kind of the energy balance equation and temperature distribution, heat flux, and how we can model that over time. In this example, I'd like to take us through a really complex chemical system in which we can start to model some of these parameters through process dynamics, right? And kind of the theory that we've been taught through the rest of our degree, let's start to take that and apply it to a chemical system. In this set of 3 videos, we're going to go through a distillation tower and monitor distillation dynamically over time. As in, if I make some sort of input change to the system, how will the process respond, right? And we'll mess with a couple things here. The main one being kind of startup and turning on the tower. And then we're going to look at what happens if we run the tower for a while, let it assume steady state, and then we change the reflux ratio. What's that going to do to our products and to our compositions within each tray? So let's get into this. I think kind of a place to start is to start from this theoretical basis of deriving the differential equations for our mass balances. And then from this, what we're going to attempt to do is kind of simulate the response of this system over time. So this video is going to be kind of some heavier theory on distillation, or maybe someone that hasn't had it as in depth of a experience with separations technology. And then in the next videos, we're going to simulate that over time and to apply a little bit of control to the system. But again, primarily at this point in the course, looking at process dynamics and how can we change, how does a system change basically with respect to time, which is something that's obviously left out of a thermodynamic analysis. So again, a lot of times in separations we look at efficiency. Here, what we really want to look at is, well, what will our system do, with respect to time, and what will each tray really look like, because that's its own little equilibrium, right? And what does that really mean? So let's start here by kind of taking a look at the system we have set up for ourselves. All right, there it is. We're looking at differential equations governing rate of change for molar holdup and mole fraction of the more volatile component in the distillation column. So we're going to assume constant molar flow rates in each section, negligible vapor dynamics, and a vapor flow to the condenser perfectly controlled to match the sum of reflux and distillate flow. We're told the liquid flow rates can be assumed to follow this equation, where we have some constant multiplied by holdup minus holdup naught, which is holdup at which no liquid overflows the weir in each stage. This ignores bubble volume and training liquid. Okay, so we got a lot of kind of terminology in here. Let's start to break that down into what are we really talking about. I think it's best to start with, hey, what's the distillation column look like? And again, this is something I actually have some experience with through internships. At this point in my career, I'm lucky to say that I got to, dive around and look at the internals of distillation up up close and personal on a large manufacturing scale. But there is some kind of janky terminology that I think is worth discussing. So when we're talking about mass balance here on our column, and perhaps maybe I should really draw the column like this. You know what? We're going to go quick. How about that? It should have a bottom as well, I guess. And there's going to be a product coming out the top. It's going to be a condenser. And for this system, we're going to go ahead and assume a total condenser, which just means that there's no extra stage up top here, and that we're only taking liquid product from each point here. So this is going to be our distillate, aka our top product, right? And so again, what are we attempting to monitor in each kind of stage here? We're attempting to monitor our mole fraction or volatile component and our molar holdup. So let's call that M. D. And D is just, in this case, all of our subscripts are really going to denote our location that our X and our M are corresponding to. So we're variables of interest here, right, are X and M, and then our subscripts are going to denote location. So again, this is a total condenser, which means we only have a liquid product. Notice I drew two arrows at the bottom of that condenser, though. We're not just taking off the product here in terms of distillate. What we're also going to do is we're going to have some liquid flow returning to the column. Let's call this L naught, because it's our top liquid, right? And it's going to return to the column. We can look at the column internals here in just a moment. But what I also want to do is draw some fun down here. So down here, what we have is a reboiler. And I'm going to denote this as kind of a kettle type reboiler, which just means that there's a liquid level present in this reboiler. And what that means is the vapor then is going to return to the column. I'm going to call this V capital N for right now. And then we also have some bottoms product here. So again, in this distillation column, we're kind of assuming we're only having two pools. A lot of the time in distillation, you can have a lot of what they call pools from the column, which just means product streams basically coming out from different trays, which again, if you have a really big distillation column like a crude tower, right, a big piece of that is getting exactly the splits that you want to have. And so you may want to pull out something that is an intermediate, boiling point difference, but you may want that to be a little bit purer than some of the other things you may not be as worried about. That's a little niche, though. We don't have to worry about that for this problem. Again, this is the bottoms product, so we'll quantify this as XB and MB here. Okay. Now, let's talk for a second about the internals of distillation. So in the internals here, what we really want to look at are a couple things. On the side of each column, of course, we have the trays, which are something you've probably heard before, right? And these trays are where vapor and liquid are mixing and then separating based on boiling point, right? That's our driving force of distillation, is a boiling point difference. So here's a tray. We're going to simplify our distillation column here and just give it 7 trays. So what that means is we're going to give it a stage there, a stage there, 1, 2, 3, 4, 5, 6, and 7. And again, I did not equally space the trays, not on purpose. In fact, what I'm going to do here is actually just kind of give this guy some space, and then draw these guys kind of as close together as I had the other ones. And the reason, of course, I'm separating that middle tray, which is tray number 4 here. Actually, well, what I really want is there to be 7 trays total, 7 stages total. And of course, the reboiler should count as a stage. So let's draw this arrow actually coming in up here. We're just going to assume that it's returning vapor onto tray number 6 there, even if that arrow may or may not show that. And so this is stage 7 because our reboiler is doing a separation, right? The same as a tray would. If we had a partial condenser, so if we were taking a vapor stream off the top here, we would also call that a tray, or rather a stage. It wouldn't exactly behave like a tray perfectly, right? But we always call those trays. Anytime there's vapor and liquid separation after mixing of those two. And so on each tray, right, what are the things that we have happening? Well, we kind of have 2 phases, right? Mixing and then separating, like I said, by boiling point. So these phases are going to have both components in them. So you're going to have this liquid, right? You have liquid coming out of here. It doesn't show up great. So you have liquid in this drum that's been condensed, right? And liquid as distillate. And L naught then is going to come onto here. And you're going to have liquid come in and come in and come in. And you're going to watch it accumulate. And then as that liquid accumulates, at some point it's going to come over this little notch here. This little notch. Right here. This is what we call the weir. Right? And so then when that liquid accumulates over the weir, it's going to start to spill down. Spilling down liquid, and it'll crash down here. And then it's going to do the same thing on this tray, and then crash down, and then build up, and then crash down, and build up, and build up, and build up, and then crash down. So I kind of went a little overboard here in drawing this liquid, so now I'm going to go ahead and finish it out and crash down here into this pipe. And then it's going to be separated here. It's going to be boiled here, or reboiled. All right, so now we've seen all this liquid happen, right? But we also talked about a vapor phase. And so I'll denote that vapor phase in what is not a hideous color to look at here. Let's see if I can find something. Okay. Let's denote it in kind of this light blue. So now that we're down here at the reboiler, we're going to have vapor start to form. These little vapor bubbles, right? And those are going to travel on up through this pipe and hopefully get back onto this tray and mix well with this tray. Right? Now, when that mixing happens, there's going to be kind of a separation by phase, right, that starts to take place. And so obviously vapor is going to be lighter than liquid. And so it's going to rise. and there's going to be tiny little holes or grates or um, there's a bunch of different basically manufacturer types in terms of what can be on the bottom of each tray. But the idea is that whatever's down there will allow vapor to come up into the tray here. Now, you'll notice I didn't draw any bubbles in this region here. And there's a reason for that. This region here is generally called the downcomer. And the idea is that the liquid is falling with such propensity that it prevents a vapor movement of the downcomer. Again, if distillation is going wrong, then you will see vapor go up the downcomer. We're assuming our distillation is going to go right here. And with a relative volatility of 2 between the components, I'll show you that in the next video, we should be more than okay. So vapor comes up, and it's going to do that for all of them. And eventually you'll have, hopefully not too much vapor in that headspace, because it's now been condensed by the condenser, and will be returned as distillate. So that's kind of the two phases that we have going on in distillation. There's a couple terms to define here, I guess, still. Again, we call this guy here the weir, but we will call this our holdup, and this liquid level will be holdup not. That looks like a theta, but it's supposed to be a 0. And so that's just two ways to kind of denote liquid height here. Again, what are we looking for in actuality? Well, what we're looking for is mass. Well, what is mass but height times area, which is volume, times density over molecular weight, right? Will give us mass. So assuming, area is going to be the same on each tray, density should be the same of each component, and obviously molecular weight of our components is going to remain constant. The only thing changing here is going to be height. So really we are writing mass as a function of holdup here. And that's going to be the idea in the equations that we derive momentarily. Okay. Let's see if there's anything else we need to define. Again, we have this W term here. Oh, I know what I need to define before we go into that. I denoted an L naught and a VN here. Stage 4 is going to be our feed stage. So here's our feed, volumetric flow rate, as well as, molar flow rate. So it's going to be in some sort of moles per unit time, as well as some composition Z. Now, once feed hits that tray, it should kind of flash or change in some way, so that we have some separation taking place. Now, we have vapor. Let's take stage 4 as an example, and I'm going to kind of conceptualize these just in terms of variables we could use for any stage, right? So the vapor that's traveling up from this stage, we're going to call V lowercase n. And the reason is, in this kind of naming scheme, we're going to assume that stage 1 to 7 is really stage 1 to capital N, with lowercase n being the stage that we are currently on. Okay. So again, coming off of a tray is going to be V sub n for that tray. Now, we also have what's going onto that tray. Well, that should just be the n plus 1, right? Um, by this convention that we're using here. So then, well, by the same convention, the liquid going down to the downcomer, I guess, um, in this case, would be Ln, and then the liquid coming from this downcomer onto the tray would be Ln plus 1. So it's important to kind of denote those terms there, simply because, as we'll see in a second, because I'm sure I will get mixed up in my words at some point, um, sometimes it's a little hard to remember that the N term for either the vapor or the liquid is what's coming off of the tray, not what's going onto the tray. And so usually I can catch myself pretty quick now because I've done this a couple times, but I do generally end up making that mistake at least once. So, distillation in a nutshell is that, again, I've denoted an L naught and a V subcapital N at kind of our extreme conditions coming on to our first and our last tray, or our first and our nth tray, right? And we've also defined liquid flowing to each tray as a function of holdup, right? And really holdup is just a height value as we've defined it in this case. So our liquid flow rate then is really a function of some constant W times how much was the liquid height over that of the Weir to the 1.5 power. And that follows from the Francis-Weir equation, loosely, I would say. Well, not really loosely, we've just combined some terms into that capital W term from that equation. But the height difference to the 3/2 power is consistent with that of Francis-Weir, which is a common correlation used for liquid flow rates in distillation when there's a Weir involved, right? So, let's see if there's anything else we really need to say about the system before we dive into the actual differential equations here. Again, we're assuming constant molar flow rates in each section, negligible vapor dynamics, which just means that our vapor is not going to change through each stage, which of course it really will be, right? Because not only is it changing composition, but there's going to be pressure drop in the column in reality, but we're not really looking too deeply into that for this system. And the vapor flow to the condenser perfectly controlled to match the sum of the reflux and distillate flow. All that means is that as soon as we start cranking that knob to turn up the reflux ratio, which will just be sometimes we've got distillate D here, on blue, distillate D here, our reflux ratio, we're just going to go ahead and define as L naught over D. Okay. I think that's all we really got to say about kind of the assumptions we're making with this system. Maybe I'll remember a couple more as I start to derive these equations. But let's go ahead and start to derive them. So again, I'm going to go ahead and derive them for a specific tray because I think that makes the most sense in terms of how we can really start to code this. We'll just make an array of masses where their index is going to be their tray, and a row of compositions where their index is going to be their tray, and then simulate that response with respect to time. But again, we'll see that in the next video. Don't want to jump ahead of myself here. Let's start with our change in mass with respect to time, because of course that one's going to be the easiest. Sorry, change in moles. We're working in moles for this system, not mass. I'm just so used to denoting lowercase m as mass. I probably should have made it something else. But can't make it lowercase n because that's our tray number for the system. Maybe I could have done dni. But what are you going to do now? 5 minutes into this video. So again, what's going on to and what's leaving each tray? If I just take a random tray that's, not tray 1, 4, or 6, or 7, I guess in this case, is really 6 should be fine. What's going to be coming out of the tray is the liquid from the tray above it plus the vapor from the tray below it minus the liquid leaving that tray minus the vapor leaving that tray. That's it. We're working in molar flow rates. We said we could assume vapor molar flow rates are constant for each section, and so that is it because we're ignoring vapor dynamics. Again, for our feed tray, we would have to add our feed coming in whatever phase that would be, and kind of splitting that into its two phases. If it were, actually, that's it for this piece here. This is only for feed for tray 4, right? But yeah, that is it. I guess if it were the top stage, you would be losing some extra amount D. If it were the bottom stage, you'd be losing some extra amount B. So this is stage 1. This is stage 7, right? So now the other thing we're going to go ahead and do is we're going to try and figure out what is dxn dt. Well, the only way I can think to find this is by doing some kind of manipulation of the product rule in this case. We know we can find composition times molar flow rate for each stage because we would just be multiplying composition by molar flow rate. So I would argue that we would just take this derivative here, and from that we would simply, what? Let's see. If we did the product rule on this, we'd say xn dmn dt plus mn dxn dt. So that implies that dxn dt equals dmn xn dt minus xn dmn dt all multiplied by 1 over mn, right? So that's what we're basically going to do here. To do that, our only unknown, assuming we know composition and the moles present on that tray as a function of holdup, we can simply say that dmn here is going to be what? It's going to be the composition on each tray minus what the vapors that are leaving, right? So let's see. It's going to be the composition coming in minus xn ln minus in minus composition times mole going out. From that, we can then say what? From that, well, obviously the feed stage would also have plus, whatever times the composition is times whatever portion of the feed, if it's multi-phase feed for that tray. again, that's only going to be 4, I should say. N equals 4, right? Now from this, we can pretty easily manipulate our variables here with a little algebra, define dx and dt, and we just say it would be this multiplied by that minus xn times, oh, yes, xn over mn times dmn dt. We solve for right here. And that is it. Now, at steady state, there are a couple kind of corrections we can make for our condenser and excuse me, and reboiler stage as well, right? So I'm going to go ahead and write those now. So when I code them, I can just rid of this. So at the condenser, right? Like I said, we're taking off a specific piece of that component. So, and again, I'm just going to do the steady state correction right here. So this will not really apply to our simulation when it's not at the steady state, but instead only apply when it is at the steady state, right? So if it's a steady state, molar holdup, and therefore mass change should be 0. Now, what's entering and leaving this tray? Well, we have L naught leaving, so that should be negative. We also have our distillate leaving, and we're adding our V of stage 1. And so that there will be our condenser molar holdup change. Let's do the same for the reboiler here. And it's going to look very similar, except the string we're taking off in this case is, well, I guess both of them are going to be liquids, right? So this one will be L capital L6, I guess is what's coming into this tray, aka Ln-1, right? We're on stage 7. That's coming in. We're subtracting the bottom's flow rate, and we should be subtracting vapor flow rate for stage N, which is stage 7, right? And so that kind of shows how we can use our equations here. Again, this isn't really derivation, but it's something I wanted to go ahead and write down as kind of our special cases, our ends. And our feed stage, of course, is going to be our special case, but that one we don't really know anymore about what we can write about it until we really see what we're trying to simulate. They have to specify the feed to some extent. So let's also look at our D, X, N, and N for our condenser. Well, I guess we could call this not, right? Because we're at the 0 stage. This is, again, above the entire system, right? So change should be 0. And what is that change really going to be? Well, it's going to be what's coming in, so y1, v1, minus what's going out, xn, or sorry, x naught, L naught minus x naught v, right? And I guess we could also call X naught XD, which is what I did in the initial drawing, but it doesn't really matter. Let's do the same for the reboiler real quick. So this will be what's coming in. So X6 L6 minus X7 E7 minus Y7 B7. And you can see kind of the difference between the reboiler and the condenser pretty clearly here now with the second equation written is, the compositions that we're taking in connection with our product streams may be the same, but what we're returning to the column, those concentrations are opposite. And obviously, the compositions of what phase is coming in are the opposite as well. All right, Risky. Let me think if there's anything else I want to cover in this video, because I think that virtually covers all of the differential equations here for those two components. Large bubble volume entrained in the liquid. So again, we could go ahead and plug in that equation for L and then kind of solve at steady state, I guess, to get back to the in our mass equation here. And so that's exactly what we would do to get kind of our steady state conditions. But I don't find that particularly necessary. I think that's fairly intuitive. And again, we were just attempting to derive the differential equations here. So in the next video, I'll simulate though from kind of starting with those derivations in hand, and we're going to simulate the response to basically adding additional feed and starting up our reboiler and condenser with each tray filled with the feed composition and virtually no holdup. So excited to see you then. Bye.